Also, there is something I posted already in the chat. Make sure that when you join, or even after you join, make sure you put your full name in your Zoom account, and that's for us also to, for the certificates. It's much easier for us to like keep track of the people who attended, and yeah. So if you just have your first name, or if you have like some other name or email, it's much easier if you just put your full name. Okay, so it's now 1:03 p.m. at least here it is, Eastern time, and yeah, so we can get started. I see the number is kind of leveling off, so I think we're not gonna miss too many people if I start off here. Also, I don't think you actually didn't mean that you have to post it in the chat, your name. Just make sure that it's your name on Zoom. I mean, it also, if you want to put it in the chat, that's fine. But just make sure that it's your name on the Zoom account. Yeah. There seems to be something unmuted, so make sure you're also muted on the thing, unless you're trying to say something, but it's probably much easier to post it in the chat. It's much easier to read. Okay, so let's see. Oh, never mind. There we go. Okay, so I'm gonna start the presentation now, and the topic for today is nuclear structuring forces. My name is Stefano Marin. I'm a student here at the University of Michigan, and yeah, so this is the second topic, the second lecture in the lecture series of for the nuclear engineering summer school, and what we're going to talk about today is the basics that kind of underline the rest of the presentations. So this is not an advanced talk. We're not going to talk about too many applied things, but we're going to talk about most of the concepts that you're going to need later on that might not be explained in detail in the next presentations. So this is an overview of the lectures for the next few days, for this lecture here. And there are three sections, so three main topics that we're going to cover. And rather than having all the questions and answers at the end of the whole talk, I think it's also one thing that I would like to do is I want to explain the first thing. So I'll go to the first section, the composition of nuclear, and then I'm going to take a couple of minutes, see the chat, check the chat, and see if there are any questions. And yeah, please go ahead, post anything, even throughout the presentation, and I'll just check the chat at the end of the section so we can address those. The second section is going to be the visual picture of the nucleus. So this is a kind of a way of thinking about the nucleus and nuclear interactions in a visual way, just to build intuition and understand the material that's going to come through the school later on. And the third part is going to be excited states and nuclear levels. Also, of course, extremely important. And one of the case studies that we're going to do at the end, if there is enough time, we're going to cover a bit of decay, so decay processes. So let's get started with composition of the nuclei. And as I said earlier, just feel free to post your questions throughout the presentation, and then I'll check them at the end of the section. So there we go. Here. Okay, well, first of all, let's talk about kind of like a very low-level thing, like a very fundamental thing, which is the interactions or the forces that we know can keep things together, the things that through which things can interact. Well, so this is you might have heard of this before, but there are four main interactions in the universe. They are written all here: the gravitational force, the electromagnetic forces, weak nuclear forces, and strong nuclear forces. And one way to think about how these things work is that they are interactions that take place between things with certain charges. So I'm sure that all of you have seen the gravitational interaction before. This is something that, you know, it's present in everyday life, and it's present, you know, even in high school physics. Gravitational interaction is basically the interaction that takes place between two objects that have a certain quantity called the gravitational charge, or, you know, this is called the mass of the particles, with some respect. And of course, what we know from just intuition is that particles or any object that carries this gravitational charge are going to be attracted to one another. This is the reason why apples fall to the earth and you know, planets orbit one another. What is interesting about that is, of course, this force here is one of the most interesting and most important forces in our everyday life. It's an extremely important force also when we talk about the astrophysical phenomena, so the universe or astronomy. But when we talk about the nuclear interactions, particle interactions, gravity actually is one of the weakest forces for the masses involved and the volumes involved. And things, gravity plays an extremely minor role, if any role at all. And therefore, we usually don't focus on gravity, and we basically never take into account gravity in our calculations or in our models. The second type of interaction that can take place is the electromagnetic interaction. Now, this is an interaction that takes place between objects that carry the electromagnetic charge. Just like the gravity, there was a gravitational charge, the mass. Here, there is going to be an electromagnetic charge, and in common language, we just call it the charge. It's so important that we drop the electromagnetic and we just call it the charge. And in this case, there are some different examples that we can do. There is actually, the electromagnetic charge can come both in positive and negative, so it doesn't have to be always positive. And as you might know, the electric interaction, so one of the two components of the electromagnetic part, is going to repel objects that carry opposite charges, say equal charges, sorry, and it's going to attract objects that carry opposite charges. So with that respect, you know, under some respect, this is similar to the gravitational interaction, but in some respects, it's very different. And most importantly, the electromagnetic interaction is much more just than the electric interaction of the Coulomb interaction. There is much more going on. It's all the different interactions that can take place between things that have any kind of charge. Moving charges will interact magnetically, and accelerating charges will emanate waves. So it's all the description of all the things that is gonna describe the interaction of things with electromagnetic charges. Now we'll cover the next two things. These might be things that you have not seen before, which are the weak nuclear force and the strong nuclear force. These are things maybe that you cover later on in an undergraduate degree. Again, just following the same template that we've done for the other two. What we have to talk about is some kind of weak charge. And the weak charge basically determines if an object interacts with other objects that also have a weak charge. And so Now, the weak charge is a bit harder to understand, or it's a bit more complicated to understand because it's not doesn't give rise to a fancy force as we interpret, for example, in gravity and electromagnetism. It gives rise more to certain processes. So two particles will undergo a certain process, or when they go some kind of interaction, if they have this weak charge. But not necessarily, we shouldn't think about this as being simply like a repulsive or an attractive force between two things. So in this case, it's more of a generalization of force. It's really like more of a weak nuclear interaction that we should talk about. And so I'm going to draw here something that is not really an arrow that determines whether two things are attractive or repulsive in each other, but simply that they are interacting with one another. The last force that we talk about is the strong nuclear force. The strong nuclear force is again mediated by a charge, the strong charge. And in this case, it's a force that holds together things that have this charge. There are, of course, other things that it can do, but for our purposes, the strong nuclear force is going to be a force that really holds together and keeps together everything that has a strong nuclear force. And just as exactly as the name indicates, the strong nuclear force is extremely strong. It's actually the strongest of all the forces. So strong, in fact, that it can win over other forces. Two things that you might think would want to repel each other, if you put them, if they interact with the strong nuclear force, might actually start sticking to one another if you manage to bring them closer enough together. Okay, so these are the fundamental forces, the fundamental interactions through which any two matter things, any two matter particles can interact. But we haven't really talked about what is matter and what are the fundamental blocks of matter. And that's what we do in this slide here. So we're gonna take kind of like a bottom-up approach where we start from the bottom and then we start to build up things until we get to the atom. And then we're gonna focus more on the nucleus in the next few slides. Well, first of all, the four particles that I want to kind of give an introduction to in this slide are the ones that make up most of the field of study for nuclear engineering. Actually, the first three, I would say, in a conventional sense, would be the ones that make up the nuclear engineering, specifically the measurement section of nuclear engineering, which are the proton, the neutron, and the electron. Although recently there has been a lot of interest in neutrino detection. Now, the proton and the neutron are very interesting particles because they actually have very similar properties. Their masses are very similar, and they both, so the masses of a proton and a neutron is, and I want to give exact figures, you can look these numbers are, but they are approximately, let me change that to an approximate sign, approximately 940 MeV per c squared. If you haven't seen these kinds of units before, it's not a big deal. Like just what we're going to look at is the relative sizes of those masses written in these units. This one here, just to give you an example, is an MeV, so mega electron volt per c squared. So if you move the c squared, it's just mc squared, and the mega electron volts is a unit of energy. And for the neutron is also approximately 940 MeV per c squared. Slightly larger for the neutron than for the proton by a very small amount, by a fraction, like by about 1 MeV actually. So let's see what are the other characteristics. So we know that this is what we call the gravitational charge to some extent, but there are also the other charges that we talked about. Well, so is the proton going to carry a electromagnetic charge? Yes. And this actually is the main thing that distinguishes the proton from the neutron. The proton is electrically charged. However, the neutron, as the name might suggest itself, is electromagnetically neutral. The proton and the neutron also carry both the weak and strong charges, so they will also interact with the strong nuclear forces. Now, this is not very important for many respects, but one of the things that it is important is the beta decay. So in beta decay is the process by which these two particles can decay into one another, actually, well, beta plus and beta minus, depending on which one goes into which. And so the decay processes of these particles actually are dictated by the weak nuclear force. So these two particles both carry weak and strong nuclear forces, charges. So this picture here kind of shows you that the neutron and the proton are very similar. They share similar masses, both have weak charges, both have strong charges, but the main difference is the proton is a charged particle and the neutron is not. Now let's look at a particle that you've all seen before, but let's look at it from the lenses of how it's going to interact. The electron is actually a very light particle. It's so light that compared to the neutron and the proton, it's almost massless. So the mass of an electron is approximately half of an MeV. Maybe I'll write the full number because it's important later on. Some people might just say 511, just expecting you to know exactly what it is. That's the actual mass of the electron to a few more important digits. Now, this mass here is, as you can tell, it's about 2,000th of the mass of the proton and the neutron. That makes it an extremely light particle. However, the charge of the electron is the same as the charge of the proton. So imagine the same amount of charge in a much, much smaller envelope. And it's the same as parts of the proton, but of opposite charge. So proton and electron will attract one another, with the electron, of course, being much, much smaller. And then we should talk about the other two charges. The electron does carry a weak charge, but it does not carry, it does not carry a strong charge. Maybe that's the best way to show it. Okay. And just maybe more academically, I don't know how many lectures in this series will be about the neutrino and the properties of the neutrino, but just to give you an example of why it is that neutrino detection is so hard, is going to be given here. The fact that, for example, the fact that the electron is so much lighter means that it's going to escape detectors more easily. The more charges something has, the easier it is to detect. So let's look at why the neutrino eluded so many detection. It takes so much effort to detect neutrinos. Well, the neutrino has a mass that, yeah, it's technically above zero, but it's basically zero. It's of the order of EVs, so 1,000,000 times smaller. Nobody really knows the mass of the neutrino, but it's predicted to be millions of times smaller than the masses of the proton and the electron. So we're really talking about an extremely small mass. The neutrino, again, the word neutral is in there, so we know that the charge of the neutrino is also zero. There are actually different types of neutrino, but something that we don't really have to worry about for this presentation. They have very similar properties. And lastly, they carry the weak charge, but they do not carry the strong charge. So that makes the particle interact only through the weak interaction and gravity, but that's really something that's never going to happen. So only through the weak interaction. So the neutrino is really a weakly interacting particles. And that's why it's so hard. And whenever you talk about neutrino detectors, you're always going to see these very large detectors because you just need a lot of matter for the neutrino to go through before it has even a chance to interact with things. Of course, there is a lot of field of study now about making the detectors smaller and better, and it's actually happening. So very exciting field. Okay, so we talked about what makes matter and also what are the interactions of matter. And now we're going to take our first case study of how to form an atom. The picture here that you see to the left is a very schematic, very much not to scale picture of the nucleus and the atom, where the nucleus, as the name might suggest, is located right here at the center. Nucleus, sorry, I cannot spell anymore. Nucleus. Around the nucleus, inside this area here, and surrounding the nucleus, is something that we call the electron cloud. Of course, quantum mechanically, we know that things do not really localize things to a specific point in space, but this is called what we call the electron cloud. That's where we have a high chance of finding the electrons. Now, what is the nucleus made of? Well, the nucleus is made of the other two particles that we talked about earlier. It's made of neutrons and protons. I'm messing up all the colors, so don't really look at the color schemes. But the nucleus is made up of these neutrons and the protons surrounded by the electrons. Now, the important thing to see, just to build some intuition, is that the electrons are negatively charged, right? All the electrons are negatively charged, so they will tend to repel one another. This structure here will, if only electrons are concerned, it's going to like try to push away each other and just going to immediately destroy. It will not stay together. However, we have this center, like the nucleus, where there is an equal amount of protons as there are electrons outside in a not ionized state, and that's where we might find. That's where we find the source of what keeps the whole thing together. There is such a concentrated high charge, positive charge at the center, that all the electrons are going to be looking at that charge and be attracted to it. And when the two charges are, counteract exactly, that's when the atom becomes stable and it stays. It becomes a stable structure. So that's the explanation of how the electrons get bind to the atom, how the electrons remain bound to the atom. But that doesn't tell us why the protons themselves remain bound to the atom, to the nucleus. Because again, same explanation that we said for the electrons, they charges that are the same as one another, they would tend to push away one another. So in the center here, we have a lot of protons, have the same amount of protons as we have electrons outside. And for any element, depending on the element, you would have more or less electrons and protons. But we usually have a fair amount of protons concentrated in a very small area. And intuition would tell us that these particles would tend to push away each other very, very strongly. However, as I said, the strong nuclear force is much, much stronger than the electromagnetic force. And if you manage to bring things that close together, the neutron and the proton, both carrying the strong nuclear force, will actually, and the proton and the proton and the neutron as well, will start gluing together. They will start sticking together and overcome these electromagnetic forces. This overcoming is always in competition. It's not a complete landslide victory for the strong nuclear force. There is always going to be a competition between these forces, and that's going to be very important. I think later on week 6 or week 5, when we talk about nuclear fission. In that case, it's actually the fission is when these electromagnetic forces win over the strong magnetic forces, and that happens when there is an excess of charge and some deformation can lead to a runoff reaction. Okay, so that's how atoms and nuclei are held together. And now let's use this picture here, as I said, very much not to scale, of the nucleus of the atom, just to give you an idea, an intuitive idea of what the scale of things are. So an atom, one good number to keep in mind, are just like units named after famous scientists. Well, an atom is approximately 1 angstrom in size. And 1 angstrom is approximately 0.1 nanometer, or I don't know why I said approximately. That's exactly 0.1 nanometer. And the atom is approximately 0.1 nanometer, and and that's approximately 10 to the minus 10 meters. Again, exactly 10 to the minus 10 meters. Now, this is a very small size. We are talking about smaller than anything you see in everyday life, smaller than hair, smaller than sand, much, much smaller than any of those things that you would see in ordinary life. However, what we have to understand is that the nucleus is much, much smaller than the atom still. So when we look at the dimension of the nucleus, we're talking in the dimension of about 1 Fermi. So that's another scientist that got units named after him. Although these units here are also called femtometers. And those are exactly 10 to the minus 15 meters. Or, if you just do the quick math there, it's 10 to the minus 5 angstroms. So if I want to draw this to scale, well, first of all, one easy way to understand is if there's a center of the nucleus here, which you can measure it on your screen, it probably appears to be about 1 centimeter in diameter. The atom itself would be 100 meters in diameter. So if the nucleus remained the same size, in order for the atom around it to be of the correct scale, it would be around the size of a football field. So just let that sink in of what is the relative size of a nucleus compared to a relative size compared to the size of an atom. So this is really the interesting part about the nuclear interactions, that they take place in such a small volume, and all these things happen in such a small volume. You know, the smaller the volume, the higher the energy to keep things together. So that's really why it's very exciting to study these kind of things. Okay, let me go to the next slide. So we now talked about atoms, and I just want to give you an idea of how to organize these atoms. We talked about like an idealized atom, which was like just, you know, electrons and protons. But you know, atoms actually come in discrete packets. They come, you know, they can be divided into very well-defined objects, and that's actually what we call elements. So I'm sure that everybody here knows about the periodic table of elements, and that's the one that is shown here. This is an extremely useful thing to have around the house in general, very useful reference to know the periodic table, and it just shows all the elements that we know about. Now, the elements are what makes up materials. So everything that you see around you and everywhere that you can think of is made of elements. And you know, their properties, for example, their density, you know, when you lift them or when you try to squeeze them, or you know, the material properties like the tensile strength, the heating conductivity, the color even, the way they look, is all determined by what element they are. This is because chemistry determines these properties, and chemistry deals with the electrons and the electronic interactions. So the electron cloud that surrounded the nucleus. And yeah, so when we want to understand these properties here of matter, the one that I write here, but there are many more, we only need to understand what element they are, how many electrons there were around it. And by knowing the number of electrons, even in an unionized state, we also know the number of protons. Now, however, there is one variable there that was left free, number of neutrons. And that's why we're going to go to the next slide. Now, let's say that we have an element, for example, let's pick an example here. Manganese. Actually, I shouldn't pick one that I don't know much about. Carbon. Yeah, that's a good one. Carbon has 6 protons, 6 electrons, and n neutrons. The periodic table doesn't tell us anything about how many neutrons there exist for carbon. It just tells us that there has to be 6 protons, 6 electrons. This is because that's what chemistry calls a carbon. In order for there to be 6 electrons in the unionized state, I cannot say the word, is there has to be 6 protons, but then there is n neutrons. And this is where the chart of nuclides comes in. And the chart of nuclides tells us how to categorize things with different number of neutrons. And the different, like an element with a different number of neutrons, so for example, carbon-12 has 6 neutrons and 6 protons, is different from carbon-14, which is 6 neutrons, 8 neutrons and 6 protons. And this will be called 2 isotopes of proton, or the element of carbon. And the chart of nuclei, which you can actually find at this very, very interesting website here, I suggest all of you for the next 8 weeks, for the part of the summer school, and maybe for the rest of your life, just save this as one of your favorites on your browser, and you know, scroll around it on the weekends whenever you have time. There is a lot of interesting information on it, and you'll see a lot of different plots, a lot of different schemes about all kinds of isotopes that you know. Stable isotopes, unstable isotopes, all kinds of things. But the chart of nucleus is a way to categorize and extend the periodic table. The periodic table only dealt with elements. Now the chart of nucleus deals with isotopes. So it has all the information contained in the periodic table, and on top of that, it has the information of the Newton number. Usually the Newton, like the chart of nuclides, are color-coded to convey some quick information just by looking at it. And in this case, the color coding is made according to their stability. So when we look at this chart here, what we're looking at is the stability of the isotope. In black, we see the stable isotope, so the ones that don't decay. And you know, based on the other colors, we see how much they decay. And you can see here that there is actually white spaces on either side. And this is because simply those elements do not exist. Those isotopes do not exist or have never been synthesized. It could either be that they've not been discovered yet, or sometimes it's just because like those things don't stick together. Like they simply don't form bound states. So when we look at something this, we actually see all the possible isotopes that we, right now in the year 2021, we know about. Of course, this might extend kind of diagonally up here. And, it might even extend a little bit on this side here. Yeah, so as I said, I refer to you to this website here. Please, it's a great reference. And yeah, this concludes the first part or the first section of the presentation, which was about the composition of the nuclei, which is maybe a bit more general than just the nuclei. And so, as I said at the beginning of the presentation, I will now start looking at the chat just to see if there are any questions. And feel free, I just see one now, but feel free now to just type in the chat any questions. I'll take as many as there are, but maybe I'll stop at like 3 or 4. So, if there are any questions about this, please put in the chat, write it in the chat. And yeah. So, okay, that's a very interesting question. The first one is, what is the color of the nucleus? That's yeah. So, well, it doesn't really have a color. The color is something that we associate with a very small section of the periodic table of the electromagnetic spectrum. It's a very selected wavelengths have colors, and those are basically the wavelengths that you would find for the very weakly bound last electrons, like the very outside shell of the electrons. So the ones that kind of cover large sizes. The smaller you go, like actually in the smaller you go in the dimension of an object, you can think about it as being an inverse relationship with the antenna size. So you can imagine that everything emits radiation based on the sizes of its dimension, of the physical dimension of the object. So if you look at, for example, the electrons in the outer cloud, they're going to emit things with kind of log wavelength, and that's what our eyes interpret as colors. But as soon as you go to something even like the inner electrons, those usually we call X-rays. And of course, we know that we don't see X-rays. And when you start looking at what color something like inside the nucleus would be, well, we're talking about gamma rays. And that's something that we do not see. So they are basically colorless. And yeah, so I mean, that's kind of an explanation. It's interesting because, there is when I was talking about the strong nuclear charges, in the lingo of the strong nuclear charges, that's also called the color. So that's an interesting connection there. Yeah, so if neutrons are chargeless, how can they have weak and strong charges? Okay, so that's the second question there. Well, we have to be careful here. The neutrons are electromagnetically chargeless, but they are gravitationally charged. They are strongly charged and are weakly charged. The reason for that is, well, I mean, that's just how things are. That's that's the explanation, is that there is no paradox in having one and not one of the other 3 charges. You can have any combination of them. And well, not exactly, but you can have some combination of those without having to incur in any paradox about being chargeless. So the neutrons are just electromagnetically charged, but not absolutely chargeless. If you want to dig further, then you would have to look inside the structure of the neutron, and you could say, what is the neutron made of? And then you say, okay, well, actually, the neutron is made up of 3 electrically charged particles. So the quarks inside the neutron would be made up are electrically charged, and they carry all the charges. So it's just that this combination, this exact combination of the neutron, actually turns out to be neutral. So the 3 charges of the 3 quarks making up the neutron cancel out. Yeah, so they in that situation, it looks chargeless, it looks neutral, electromagnetic and neutral, but in reality, some of these effects do arouse and are very important in some application. For example, because there is a structure inside that is charged, there are going to be some properties that you can probe with strong enough fields. So for example, the neutron will respond to magnetic fields. And yeah, so that's a very interesting thing, the structure of the neutron, like what does it actually look inside. Okay, so it looks like that was the last question, or maybe 15 seconds. Okay, there we go. Another question. So since the neutron and proton have higher masses, can we conclude that the nucleus is heavier than the electrons? Absolutely, yes. Very good point. Most of the masses of things around you in the universe, like if you were to weigh, what is matter in the universe, in this room, mostly the masses of those would be protons and neutrons. The electrons would contribute very, very little amount of energy, of mass to the thing. So most of the mass, most of the pounds that would make up an object is actually comes from the protons and the neutrons. Yeah, very good point. Color charge. Yeah, I don't know if this is the right setting to talk about color charge. It's really once, what we deal more in nuclear engineering is more like the interactions of neutrons and protons with matter. So things that you see in everyday life. Now, color charge comes in when we want to talk about what's happening inside a proton or a neutron, or even what if we want to really understand what is the nuclear force. If we want to really understand what is the nuclear force, we have to start talking about what is being exchanged. The nuclear force, as we explained it at the beginning, I said it's an attractive force, but that's in reality, it's also itself is an interaction, like the weak nuclear force. And the way the proton and a neutron kind of connect together is by exchanging what we call a pion or mesons. There are different mesons, including a pion, that's probably the most famous one. And the color charge is just a way to account these a conserved charge. So the color charge, there are, instead of just being plus and minus, there is actually 3 directions that you can go in. So that's why they chose the way color. As you know, primary colors, red, blue, yellow, but instead I think it's green. So there are 3 different colors that you can go in. So instead of going right, positive, left, negative, you can think about, you can go in these 3 possible directions. And it turns out that you always have to end up with nothing. You always have to end up with no charge. You always have to end up at the center. So for example, the proton might, might have 1 red, 1 blue, 1 green, and in the end, you combine these 2 things together, you get white. Or you can get 1 red and 1 anti-red, and you get white again. So, or the 0 color charge. So that's just a way to keep track of this conserved color neutrality of everything. And it's a very nice mathematical description, but it's a bit beyond, I think, what's needed for the next few lectures. I do encourage you to, of course, read up on this if you're interested. Okay, so I guess I'm going to move on to the next section. Of course, if there are any questions about the previous section, just ask them in the next section. So the next sections are actually going to be a bit briefer. So especially the last one is going to be a bit briefer. But yeah, so if you have any questions about this, don't feel like you only have to ask questions about the next stuff. Okay, so we're going to go into the visual models of the nuclei. This is going to be a very brief explanation. This is going to be by no means a complete explanation, but I'm just going to give you ideas of how people can think about the nucleus, and give you a bit of the lingo that you might hear. Now, the first way to think about the nucleus is that the neutrons and the protons actually are very close together, and they form almost a liquid. They form like a nuclear liquid. And this liquid gets squished, like it's incompressible, but can change in size, and it's charged, and it has a certain surface tension, everything that we know about a liquid. Imagine really just a drop of water in the on a table or something. And what is interesting about it is that this liquid model was very successful in the very early age of understanding nuclear structure, and that's it because it predicted like a very nice property of a nuclei, and that's summarized right here on this. It's summarized right here in this inequality, which says that a mass of something that has a nucleons, so A could be 20 protons and 30 neutrons, it would be 50. A would be 50. Is actually going to be less than the mass of each constituent. So the mass of the collective is less than the mass of each constituent together. You weight all the components, you bring them together, and now some masses disappeared. Where has that mass gone? Well, that mass has gone into energy, binding energy that keeps the thing together. And we know maybe Einstein's most famous contribution is E is equal to mc squared. That mass got converted to energy. And one of the most important things was people trying to understand well, how much of this mass was converted to energy? How can we determine it just from looking at the properties of the nuclear, like something that we can measure about the nuclear, usually just the masses and the charges of the nuclear? Well, some people came up with this equation. This is called a semi-empirical mass equation, or the liquid to a model equation. And these parameters are usually just fitted to experiments. They're not really determined from theory. And it basically describes the nucleus as if it was a liquid drop up to a certain point, and then it just starts adding stuff that, electromagnetic stuff, and then it starts adding really quantum mechanical and very much nuclear terms. So let's start with the terms that are easy to understand. So how is this thing held together? Well, there is going to be what we call a volume term. The protons and the neutrons, as I said, they attract each other. So the more of them there are, the more they're going to attract to one another. And so there's going to be a term that tells us, the more matter you have, the more the attraction is going to be. Then we have with this term called the surface term. This is because we have to take into account that there are going to be some particles that do not live at the center of the nucleus, which are surrounded by things and really held together, but they're living kind of at the surface, or closer to the surface. So the more surface I have, the more particles I have that are more weakly bound. And that's why it's negative. It subtracts off to our assumption that everything is surrounded by matter. Next up is, you might recognize that form from other classes, is the Coulomb term. This is the term that tells us, as I said at the beginning, the electromagnetic interaction, yes, it's overpowered by nuclear forces, but it's not completely overpowered. It's still there, it still competes. And this tells us if I have a proton here and a proton here, how much are they going to push away? They're still competing. So there's still going to be some kind of force to push the two things away, the two particles away, and it's trying to lower the cohesion of the particles. And then we have the two next terms, and these terms here are a bit weirder. Of course we can understand them, but it's not really here the setting to. The next term is called the asymmetry term, and that tells us the way that these neutrons and protons are going to be. They're going to start populating levels. They all have to have different properties, and it's much better if for every neutron I put a proton and neutron and proton like that, rather than start putting too many of one particle type. Because if I start putting too many particle types, I'm going to start to have to give out more and more and more energy to each particle every time. So this tells us that the most stable ones are going to be things that have about the same amount of neutrons and protons, and the most unstable ones are going to have an excess of one or the other particle types. However, we should say that this is in competition with the volume term, because I can increase the volume just by adding a bunch of neutrons and get some energy from that. However, I'm now increasing the asymmetry term. So all these terms, really, there is a lot of competition, a lot of correlations between them. And then the last one is the famous pairing term. This is something that tells us that when protons and neutrons, they really like to couple up together. They really like to pair up with one another. So even terms, even numbers of neutrons, even number of protons, they really love it. So they're going to really try to stick together. And that's the reason why we have this extra term that takes into account the parity. Well, no, let me not use that word. The evenness of the nucleus, and it tells us that the most stable ones, the best way to do it is even number of neutrons, even number of protons. These are the famous even nuclei. People are always going to talk about even as being like very stable nuclei. So examples could be molybdenum 104 or carbon 12. So these are even nuclei. And then you have even odd or odd even, depending on whether it's the proton or the neutron that is an odd number. And those are less stable. They're significantly less stable. But they're not the worst one. The worst one are the odd. Both the neutron and the proton are odd, and that really leads to all kinds of just very unstable, terrible properties. Very hard to study. So yeah, usually when you ever want to understand things from want to do a quick calculation just to get an idea of things, you just say, I'm going to focus on even, and that usually simplifies your mind. Of course, if somebody asks you for an even odd or an odd, then you have to do it. Okay. This was the first one was the just talking about the liquid drop model, understanding the nucleus as if it was just a liquid, like a drop of liquid. Let's now switch our minds. Like, let's now completely, put a hold on that idea and say, okay, let's think about this in another way. And the other way we're going to think about it is the shell model. Now, in the liquid drop, I hope in your mind you got an idea that all these particles are like squished together like water molecules, kind of like grinding on one another continuously, like really like a fluid. In the shell model, we're going to think about things orbiting. We're going to think about things like in the solar system, a lot of space between things. A neutron orbiting a proton and all orbiting the center. And, just imagine the usual picture that people draw when they talk about like orbits and shells, like, orbiting like that and stuff like that, with very much space between things, a lot of space between things, and going in around one another. And here, the most important thing is not the collective motion, it's not how you squish things together, but really the protagonist of the shell model is the single particle. So sometimes, the shell model is also, it explains very well the single particle state, single particle configuration. How does a single particle outside of the whole nucleus determines the whole property of the nucleus? And the reason why this exists is because nucleons, which are actually a word for both neutrons and protons, I hope I said that earlier, nucleons are, they fill up shells just like you imagine from chemistry, from atoms, and they're going to fill up shells. And when a shell is complete, you are going to have a zero, the properties, many properties of angular momentum, that's probably the most famous one, are going to zero up. So the base state, the core that's made up of a full shell, is basically not going to give any interesting properties. And the only thing that's going to really give properties is this valence nucleus, the stuff it's outside a filled shell. Now, there are different types of valency for nucleons. For the shell model, I mean, that's also similar to the atomic one, but the valency could mean like, what do you mean extra with respect to a shell that could be made up of 10 nucleon or a nucleon, like a certain number of fixed nucleon, or do you mean unpaired, as in they don't have an extra partner? It's like the odd nucleon out, and both of those actually give rise, can be described by the shell model, and they have to be taken into account in order to describe the properties of the nucleus as a whole. And just in general, like a simple visual picture of the shell model is to think about complete shells plus particle. And if somebody asks you, what are the properties of this nucleus? You just say, well, let me know the properties of this particle, and I'll tell you. And also some interactions between this particle and the core, but really puts the extra particle really in the center. And one of the greatest achievements of the shell model, just like the liquid drop, the greatest achievement was this description of the mass formulas and other things, including fission. For the shell model, the greatest achievement was the description of the magic numbers, very important things that describes the stability of things as a function of their masses. And so these are the magic numbers. It means like when I have 2, 8, 20, 28, these are numbers that you see here, 28 or 50 protons, or even 82 protons, then I get what we call a closed shell, like an even bigger than a shell, like a closed supershell. Things really pair up very nicely, and it takes a lot of energy to go and add an extra particle. And those things are extremely stable. So you might think, you might find the isotopes that have these magic numbers, of neutrons, or magic number of protons, or even doubly magic. Both numbers of neutrons and protons are magic, and those are usually like stable in an island of instability. So they really changes things. The shell model can describe this very interesting property of stability because of number of particles. Okay, the last thing here is the collective model. So the collective model may be a bit more complicated than the other two because it's really a combination of the two. It's a very general one. I think probably this is the one of the ones that a lot of theory papers about nuclear structure start as with. It's a very nice and advanced starting point. And then, of course, there is other things that can be added on top of that. But this is a very good starting point for the description of the nucleus. And basically, without going in too much detail about the collective model, just for you, for you to be on your radar, that you can look up afterwards. the collective model kind of takes the best of both worlds, combines the two together. The nucleus is made up of shells, it's made up of single particle states, but it's also treated as a rigid body that can rotate. So you can now describe very quantitatively the properties of the nucleons, not just like the masses and overall properties. You can describe quantum mechanical properties such as energy state, which we're actually going to talk about in the next section, in terms of the rotation of this liquid drop. And the liquid drop, very importantly, can now be deformed. You can start making deformation. For example, there's a very nice picture of a deformed nucleus that looks like a pear. They actually call a pear-shaped nuclei. And on top of that, you have a single particle state. So in this case here, what this picture is describing is a pear-shaped nucleus paired with a particle that's on an outside shell, a single particle state, and this whole thing is rotating. So this collective model is a very, very powerful way of thinking about the nucleus. And if you want to approach this, you would want to say, okay, let me think about both of the earlier ones, liquid drop and shell, and kind of combine them together. And then, of course, read the literature about people who have done work on this. Bohr is probably one of the most important ones. Bohr. So, okay. Next two very quick slides on this. We are just gonna explain this, but just basically like an aside. I didn't really know where to fit these two slides, but I did want to cover them because it's gonna be important for the next few things. And these are scattering processes. And these ones here basically describe, I want to go through what are the difference between a Neutron interaction and a gamma ray interaction. Basically, in a Neutron interaction, what we see is based on the charges that we explained at the beginning, based on the interactions that we outlined in the beginning, the neutron is going to pass through the yellow part, which is the electron cloud, unaffected. It's not going to care that there is any electrons. The neutron doesn't care. So this is the neutron right here, of course. And it's going to pass through everything that doesn't share its strong charge. Electrons don't have a strong charge. Neutrons don't have electric charge. They pass through unaffected. And then they hit the nucleus. The nucleus does have strong charge. And in that case, they interact with that and they knock it off. Now, I mean, several things can happen. I mean, in a scattering process, you can think about that they knock this nucleus off. The nucleus starts traveling off, loses the electrons, and it becomes an ion. And the neutron can be recoiled. So this is the way to think about the neutron scattering process. The gamma scattering process, however, is a different one. We didn't even talk about gammas in this presentation. I thought, I thought about explaining a bit of gammas, but I think it would get too complicated talking about like what is matter and what is not matter. So in this case, just note that gammas kind of carry an electric charge. So they mediate or they work with the electric charge. So in this case, the gamma can pass through the electron, and in this case, it doesn't pass unaffected. The gamma itself is uncharged, but it doesn't interact with charged particles. So when it sees an electron, it's going to interact with that and scatter off. And what it's going to do is this electron is going to fly away, and the photon could also, this gamma ray is also going to be scattered away. That's what I show here in the second plot. And very importantly, also it can leave like an unfilled shell behind, and that's how things. When there is an unfilled place in an atomic shell, things are going to start decaying and can start emitting photons. So, this is the two processes of scattering. This is just a thing that I wanted to put at some point in the presentation, just for you to, later on, you can come back to this if in one of the later slides about detection, you ever see them. And with that, I will go to the last thing, but before, of course, I'm going to check the chat. And that looks like there are 3 questions so far. Please, if you have more questions, I'll probably take 4 or 5 max. And I want to keep this to within like 75 minutes, the whole presentation. So I'll try to get to them. So don't be discouraged from posting. Okay, does the asymmetry term have some effect for light? Have the same effect for light and heavy nuclei? No, I mean, by its very definition, well, that's why it's a semi-empirical mass formula. Now, if you wanted, like the semi-empirical mass formula does have like coefficients that are fixed, and you kind of have to yes, in the formula, it would be very similar between light and heavy nuclei. But in reality, you're right. In a heavy nuclei, more of the levels are filled and the next one is higher energy. So it would be a greater effect, but it's actually kind of, I don't know if it's a random, but I would say on the average will be a greater effect for the higher, like heavier nuclei than there is for light nuclei. But this is like a minutia, I think, like if you just try to get an understanding, like just an initial understanding of how things work, then just thinking that there is this term here is fine. But yes, it is a good term that most of these coefficients maybe should depend, it's a very simple way of understanding. So there's probably more to it than just that. Of course, the term, like for example, heavy nuclei are usually not spherical, but here the surface term is assumed to be spherical. So there is a lot of things that could be improved. And I mean, in real research, you would, but just to understand it, good mental picture, it's fine. How do nuclear models cover magic numbers? So that's what we talked about in the slide about the shell model. And basically, how we said that this is a single particle configuration coupled to a core? Well, let's look at the picture to the right. I didn't really use this figure, so we can really use it now. We can see here, for example, that you start with nothing, right? And you start with just empty space, and you say, okay, let me start putting protons in this place. And you start with a proton, and the proton now doesn't like to be there because it's not paired. So things, as I said, like to be paired up. So oh, my internet is starting to crash a little bit. I hope, let me know if there is any problems in the internet in the chat, but otherwise I will proceed. And yeah, so I add another proton to make the first one happy, and I now get two protons that are happy together. And this is how I get my first Newton number. This is called a closed shell. It's a shell in the meaning that these two things like to be stable together. Then in order to get to the next shell, it's not enough for me to add two neutrons, because now these two neutrons are going to orbit around the first two, and this orbit is going to need to have many more protons in order to completely fill the space, to completely fill the configurations that are possible. So in order to fill the next shell, in order for the nucleus to get to another interesting condition where everything is paired up and neutral. So imagine one thing going in one direction, the other thing is going the otother direction. Overall, the overall picture is neutral. In order to get that state there, I need to add not two protons, but I need to add 6 more. And that's why the second magic number is 8. The next time I have to add 12 more protons. Now the extra shell, the first two are right there. The second one, you may imagine like 2, 1, 2, 3, 4, 5, 6, and then there is 12. Well, I'm not going to draw 12. Is it 12? No, close. And and you start combining things and start building, but now every time you start to build up, you're going to need a bit more particles. And that's one of the greatest discovery here. This is advanced, but like really beautiful stuff. Somebody realized that one of the shells from above, like one shell that was somebody expected to be higher, actually gets this contribution that contributes to a lower term. So there is a shell that's built up very unintuitively of just 8 protons. And that's one of the greatest success of the shell model, was to predict this small contribution, this small shell made up of 8 protons there. And then as you build up and up and up, you need more and more particles to build up. So that's how you explain that. And of course, the protons themselves, in this case, we just talked about protons. The same thing can be built about neutrons, but in real life, you would have to do both protons and neutrons at the same time. All right, maybe that was a bit of a longer explanation, but I hope that answered it. What determine which model I use? Because there are 3 in number that you discuss. Yeah, so I would say depends on what you want to do. If you are trying to get, depends on the accuracy that you want something to do. I mean, Niels Bohr famously explained the nuclear fission using the liquid drop model. And that was really interesting, like one of the greatest papers. If you in 2021 try to explain nuclear fission using the liquid drop model, that's the old news. No, that's not accurate enough. So you probably don't want to do that. But if you start to do something new research that nobody has ever done before, and you're trying to give like some idea of why it could be true, why it's valid, you can even use the liquid drop model. Shell particle, that's used actually quite a lot. There is much more lingo than I introduced. There is like how these shells can be labeled, and like the orbit, the spin orbit, like all the stuff that comes into like really understanding this more. But yeah, that's used actually in nuclear structure, that you can use the shell model if you're really focused on this last particle. In research, how you ask which model should I use? Well, if you're starting to do research that's really about, if you want to do accurate research, I would say starting from the collective model is probably the best way. Starting from something that's very complete, and then on top of that, these are still academic models, but then you might want to improve on them even more. Start adding extra terms, and I mean, these are known. So if you're trying to find something that is unknown, you might want to add other things as well. So just to summarize, I think the most the most updated one, the most reviewed one is probably the collective model. Shell model is also very much very much used. Liquid drop is probably mostly academic at this point, but it's very good for us. Like for us now in this lecture. Do nuclear models allow for geometries other than tear shape or football shape? What about super heavy transition nucleus resulting from a transition of two nuclei? Wow, okay. Yeah, I mean, that's way above this level here, but do nuclear models allow for that? So do these nuclear models, like, would I be able to describe a dinuclear system? That's what you're describing here. When the two nuclei cross each other, there is a small region of interaction, a small window where the two nuclei interact with one another. Using one of these models here, well, to some extent, actually, you can use the collective model. You can use that to describe a lot of deformation. So it doesn't just have to be the pear-shaped, football shape. You can use that to describe, for example, to less extent. In those situations, actually, more statistical models are used. And, for example, in fission, that's kind of my research. That's actually, in that case, we use more classical models like nucleon transfer in the neck. And it's definitely a more complicated, discussion. These interactions, especially because they are not stable. Their dinuclear systems are not really something that you can observe for a long time. So it's not equilibrated thermally. Very hard to discuss, but that's a very good question. I'm sure some states can be described by that. There are some quantum numbers, some very like macroscopic properties. Well, macroscopic, but still quantum properties of the system that can be described, but only like a couple of things. In a lot of these applications, I think you would want to go with a computational model, right? Like really just model the Schrodinger equation for all of these particles. That's a very complicated process. So in that case, maybe the systematic simplification might not work as well. Okay, I'm gonna go like just fast one after the other just to answer fast. Was the last slide from quantum scatter? Yes. In Newton scattering, what does the Newton interact with in an atom? The nucleus. So the nucleus is protons and neutrons, and those are both strong charges. And so that's what it interacts with. And yes. Okay, same at Stern. Is anybody? No, okay. Everybody has a, looks like, sorry, I was reading now the chat and it looks like everybody is now back on board. Okay. So let me now cover for the next few slides. Just again, very briefly, by no means a complete explanation, but there is one important thing that we did not talk about, which is just briefly mentioned, which is the energies of a system, the energies of a nucleus. And yeah, so what is the characteristic? What are the characteristics of a system? Well, in classical mechanics, I don't know how much classical mechanics or how well you like to talk about classical mechanics when understanding other systems. There are really a few different properties of a system that characterize the whole thing. There are 7 of them. And those are the energy of a system, the linear momentum, and the angular momentum. So let's think about them more now from the nuclear perspective. Let's put them into like our picture, the way we want to think about them. And the energy of the system, we're going to think about it as the heat of the system. The nucleus is going to have some heat. There's going to be some energy stored inside it. You can think about it as being maybe, you know, a rotation of the whole system, like the water from the liquid of water is heated up. Okay, that's one way of explaining it. That actually works somewhat well when describing a neutron emission. Or you can think about in the shell model, like these particles are moving faster. Okay, that's one type of energy. There is also a linear momentum. So this is how the nucleus moves through space, you know, goes left to right, up to down, stuff like that. That is very not interesting. To us, the fact that it moves doesn't really tell us anything about the nucleus itself. That's, you know, we can always exclude that and say, okay, let's move with the nucleus. Let's jump on the nucleus frame and just look at it as it's stationary. So linear momentum, really not that interesting for the characteristic of nuclear. And angular momentum, very important. Angular momentum in quantum mechanics describe the shapes of things. So that's why before I made such a like an important point about describing the shapes of stuff, you know, and also in my explanation to the football and pear shape, the angular momentum is really what determines the shape of the wave functions. So that's and you know, not only that, it's an extremely important thing that regulates gamma ray emission. It regulates all kinds of observables are going to be affected by angular momentum, and it turns out it's very hard to measure. So it's much harder to measure than the linear momentum, like not even comparable. Linear momentum is easy, everybody can measure that. Angular momentum very hard. Yeah, so these are kind of the characteristics of the system. And the linear momentum, of course, how it moves to space. Angular momentum is how it rotates, how it looks. And yeah. So how does that relate? Well, now let's look at the how to excite a nucleus, how to take something that has a certain shape, or like something that just like a nucleus in front of us, and make it have more energy, or how to excite it, how to get it away from where it wants to be. And that's going to be our the two ways that we talk about. And of course, there is many more ways of doing that. But two ways that we can talk about it is by, in the shell model, we would take one particle and put it in an upper shell. So we will leave behind an empty shell, and we just take this particle, you know, they're orbiting like that, and it just jumps to a higher orbit, something that orbits in a different way, maybe with more energy. Well, absolutely with more energy. That's what the excitation is. And yeah, so this is an excitation, a single particle excitation of the system. It's just jumping from one lower orbit, maybe smaller, not as high energy, to a larger one with more angular momentum, more energy. And it's going to take some energy to do that. And as soon as this happens, it's probably going to want to jump back down and meet a gamma ray. And so that's very similar to how we think about atomic excitation. But then there is another thing, and this is more interesting. These the wave function of nuclei is deformed in some situations. And because it's deformed, it can actually, when it rotates, it looks different from different angles. And it's very important that it does, because that's the reason why we can describe nuclear rotation as giving it an excitation. So there is an excitation involved with the rotation of the whole system as a whole. So no particle are actually changing their position. There is no jumping between states, but there is a rotation of the whole system. You know, the whole nucleus now rotates along an axis by which it looks different. And let me check if that axis is actually correct. Well, it's probably one that would go, you know, I don't know if I made drawing correctly, like clearly, but it's an axis kind of come from out the page into the page, and the nucleus would go like that, so it looks different as it rotates. You know, you don't want to pick one in which, like, as it rotates, it remains the same. And then just the most important thing to understand about excitations is things that are excited will want to de-excite. Things in the universe don't like to be excited. Things like the universe is very lazy. It always wants to have the least amount of energy, least amount of angular momentum. So always in what we call the ground state. Everything tries to go down to the ground state. So if you put a particle in a higher energy state, it will try to go down to the energy state. You supply delta E to do that, it's going to emit delta E to do that. The rotations here, what's it going to do? Well, similar thing. It's going to start emitting gamma rays in the opposite direction to slow down. And then it's going to slow down completely. Most of these things, the excitations are going to proceed by gamma ray emission, but there are also a lot of interesting applications in which there is so much energy that the nucleus doesn't want to wait the time that it takes for gamma ray emission. You know, it's not an efficient way of losing energy, but sometimes it's the only available one. And sometimes it's like, you know what, I'm going to lose part of myself it's going to emit a neutron or emit a proton in order to lose its energy. And that's like very extreme, not extremely extreme, but like more exotic situations in which the nucleus prefers to lose a part of itself to de-excite to a lower level rather than just emitting gamma rays. And that's, of course, where we see neutron emission and gamma ray emission. That's very interesting stuff. Yeah, so one interesting thing when we're talking about that earlier, I guess maybe from the shell model, it was more, it was more apparent, but the other one, an infinite amount of energy, I could rotate at 1 hertz, 1.5 hertz, 1.55 hertz. In reality, because in quantum mechanics, we have to understand that the angular momentum is quantized, so it only comes in very discrete packets. We don't get to rotate at all the frequency we want. There are very discrete frequencies that we get to rotating, and all these things together, the shell structure, the fact that the rotations are also quantized, leads to the idea that the energy levels are discrete. So you can be, for example, in these schemes here that I found from the beautiful website, wonderful website that I shared at the beginning, the NNDC chart of nuclei. Those things here are showing the energy levels that you can be in with associated angular momentum on the right. There is an extra term there, it's called the parity. That's more complicated. It's about how it looks like once we reflect the space, but that's not something I think intuitive. It's like it's not really a classical counterpart to that. But basically, you see there are levels, and the first one is down here. Then you get the second one, then you get the third, and the nucleus cannot be here. It cannot be, I want to be in between the two. It can be a superposition of the first and the second, but it cannot be in the middle. And what we see here is actually bands. This may be more advanced. I think maybe even the people who have taken some undergraduate nuclear physics might not have seen this kind of discussion. The bands are actually the rotational bands. Is I have a nucleus and it has a certain shape, and now each of these levels here represents a different rotational velocity, if you want, and a different angular momentum of the system. And so, the first one rotates slowly, the second one a bit faster, but always at discrete level. And the ground band is the one where it's normal. Maybe the band 2 could be the one in which it's a bit deformed and rotates. So it's combining two things together. Band 3 could be like deformed in one situation, maybe vibrating in the other, and then rotating. So you can combine all these different degrees together. What do the nuclei want? As we already said, they want to de-excite. So that's actually something I covered in the last slide. And yeah, I mean, that's actually kind of covers the whole thing. And I think, yeah, as I said, this is the last part. It was very brief. But now we get to the question. So maybe I went too fast in this part here. I didn't cover too many details. So please let me know in the comments in the chat if there are any questions. Okay, I'm gonna start reading the chat maybe for the next 7 to 10 minutes, and so we can finish around 2:20 before 2:30. And post as many as you can. And if if it's a good question, like I may even send you an email or send you a reference, I'll put it in the chat. So if you stick around after that, I can describe those. Okay, do the excitation events just described earlier occur simultaneously? Yes, that's actually something. Maybe it was posted before I got to this slide here. Yes, for example, the ground band here could be it's just the nucleus in this state here, like the first one. This is called the ground state. And what is the second level? The second level, it could be this whole nucleus rotating a little bit, so rotating at a certain velocity. And this one here could be the nucleus rotating twice as fast, and this one here 3 times as fast, like that. Okay, this describes the ground band. How about the band 2, the second band? Or it's the nomenclature in this kind of bands is very confusing. Sometimes they call it the second band, sometimes it's called the first excited band. So you just gotta know what you're talking about, and there is no confusion. So let's call it the first excited band. Well, in order for these energy levels here, this level of the nuclei could be, I don't know if they are, I didn't look into, what is it? Strontium 1999. I didn't look into that one too close. I just want a nice picture, but it could be, for example, a nucleus where one of the proton that was here, or one of the neutron that was here, jumped to a higher orbit, and maybe this orbit here has more of a funky shape like that. And now the rotational properties of that are different. And now we rotate this object here. And now we create those three states. So you can combine them, and that's how you create the different levels. And the last one could be, for example, the same nucleus. Now it's two particles that are excited, they are excited to a higher orbit, in a way similar to that, to this one here. Or it could be, well, it could be many things. It could be, so yes, they can of course be combined together. So yeah, very good question though. I hope that answered it. During atom de-excitation, is it always gamma rays emitted, or it could be X-ray? Okay, let me think about what I want to say here. During atom de-excitation, so let's think about the atom as being made up of electrons and nuclei, and when the electrons de-excite, that's how we get visible light. When it's a very far away, I mean, you know what? To answer this, I want to maybe even use a nice light, because it's a nice way of thinking about, like, why do we have different types of photons? Why do they always come at different energy? So let's say that this is the outermost electrons. Let's say this is the, coming back in, all the way down to the nucleus. So in this case here, these are not nucleon orbitals, these are atomic orbitals with the nucleus right there at the center. When the outer electrons de-excite, the valence outer electrons, the last few electrons, when these are de-excite, most of the times they give rise to visible light. This is why we see stuff. This is why this table that you cannot see is yellow, brown, and so that's the reason why we have those type of photons, the very last electron. If I start going closer and closer to the nucleus, very boundly, very closer, much closer to the nucleus, maybe the first, the second, usually the first and the second levels, we start getting X-rays. Maybe I should even say, if you are in between those, you get UV light. You might even get infrared light up here, by the way. So UV light in between, not super close to the nucleus, not super far from the neutrons. And in between, you get X-rays super close to the neutrons. And then when the radiation comes from the nucleus itself, these are always gamma rays. And these are not always gamma rays because the energies correspond to the gamma rays. Because by definition, if they come from the neutrons, they're gamma rays. The nucleus, they're gamma rays. And if they come from the electron cloud, they can either be X-rays, UVs, like that. So it's like a, it's like a tautology. Like if they come from the nucleus, they are gamma rays. And now it turns out that, gamma rays are usually high energy. So one thinks about the gamma rays energy being higher. But there are some X-rays that can be very high energy. I cannot tell you on the top of my head if there is an X-ray that is higher than a gamma ray, but I would imagine so. Actually, for sure there is. Yes, never mind. There is 100%. So there are X-rays that are more powerful than gamma rays. So yeah. How does the liquid drop model de-excite? How does the liquid drop model excite? That's the interesting question. And then if you understand that, then you can de-excite. I guess, how does de-excite? You can imagine that as being the that's why the liquid model is maybe not the best way to understand this. The liquid model might excite by changing shape, but then again, it would be more like a collective model in that case. The liquid drop is kind of basic, and I might be wrong on this, but I don't think it really is advanced enough. Like that equation that I showed there is, or that framework, is not really something I can account for that. That's more like single state, or like shell configuration and collecting model that determine those. So the liquid drop model, the exciter could be, yeah, I mean, that's okay, never mind. We didn't talk about decays. The liquid drop model does predict the decays. That's something probably we don't have time to do today, but I will post these pictures here. And maybe one of the questions is like, can you explain decay? Then I can get to those two slides. But yeah. So the liquid model, let's just think about it as being a bit too simple. It doesn't really explain levels. It would be really hard to explain levels to the liquid model. And for that reason, you would also not be able to explain the excitation. Can we actually calculate the probabilities of the simultaneous events if the system absorbs energy? Wow. Yes. Yes, we can. Yes, we can. If you know the energy of the ground state, which is usually zero, if you take zero, then you come in with a gamma ray, and the gamma ray is going to take in some angular momentum. You can calculate the probability of absorbing the gamma rays and ending up in a certain state. And yeah, usually there is going to be, I think that the question is very well phrased. There is the probabilities, and then we're going to be, if I do this, this is going to happen. It's going to be, if I do this, then I'm going to create, it's possible it's going to be here or here or here. And yeah. Let's see, you can think inelastic scattering for better understanding. For the liquid drop model, I guess if the neutron kind of passes through and messes stuff around and then leaves a gap and it can be emitted. Again, maybe I'm not really an expert in liquid drop model, so I've just seen it for a very simple explanation. And can you actually, yeah, so that's I think those are all great questions. About these different levels. Oh, yeah, there we go. I talked about these different levels of these different schemes that I showed here. This is one nuclear with different levels. Well, in reality, the ground state is not zero for all of them. There is going to be this mass difference that I talked about when I talked about the nuclear, the liquid drop model. So there's going to be a mass defect. Like the mass of the total is not the mass of the components, it's likely lower. So there's going to be some mass defect between things. And that means that sometimes, instead of decaying down, vertically down, you can say, well, it's actually better if I decay by going right. I change my constitution and I go and become something else because those states are lower in energy. And then I put here just two arrows that can go to both lower levels. So this would be like, nucleus XA, and this would be nucleus X or YB. And depending on the type of radiation, there's going to be, we can determine what XA and YB are. Sorry, YB are from XA. And the very interesting thing is that gamma, the three types of decay, most important ones are alpha, beta, gamma. Like very interesting way of thinking about them. It's just alpha decay, emission of an alpha particle. Beta decay, emission of an electron, or beta particle, which is an electron, and a neutrino, and and the conversion of something inside. And then you have like gamma decay. However, I should say the gamma decay is not really something that we should think about as being a decay that's something transforms from one object into another by gamma decay. Gamma decay usually happens in stuff like that, in a way where R here is either alpha or gamma or beta, so alpha beta decay, which is then followed by gamma. And so you can always think of the gamma decay is usually in coincidence with something else. It happens shortly after, sometimes not that shortly either, shortly after the another type of radiation. So it's usually this thing of going down, vertically down, but it doesn't let you change things from one type of radiation to the other. Just to give like a practical thing, again, from the same great website, NMDC chart of nuclei is a nuclear decay scheme. You can find those are very fun to look at. And you can see here, for example, this same isotope of before. You can see how it would decay to a different level than the first number there. Second number is more of like an academic theoretical prediction from that tells you how forbidden something is, how much should it happen in real life. And you can see here that these the intensity in percentage sign tells you how likely it is to go to either of these states. But let's say that I go to one of these states. Let's say that I do happen to go to this state here. What's going to happen afterwards is that I'm going to start emitting gamma rays. It could be one, it could be many. So yeah. probably, well, it could be one. Sorry. Well, 400, yeah, it could be one. So yeah, that's just one way to think about nuclear decay. And I think with that, I think I'm gonna conclude this, and I'm gonna maybe wait up here 5 minutes for everybody to post any questions that they might have, and otherwise, it was really good to teach this, and yes, I will post my. There we go. I'm gonna put my email here, and I also, it's online, everything. So, but yeah, I'll that's my email. Maybe. Yeah, I mean the one that was just there is my email. I hope that makes sense. And yeah, it was really great to teach this. I hope all of you, attend as many of these lectures as you can. And if you have any questions, these slides here are going to be uploaded online. You can always go back to that. I always really encourage you to take this as a starting point, not really as an ending point. Yeah, once you go to this, once you look at this stuff here, then you can start Googling stuff and you can start finding more references. And you'll find there's so much done. So I'm sure that you're really going to like this. Yeah, and I hope one of the I'm going to plug one of the presentations that I really like in the thing. I hope you come to the Fusion Week, and if you like this presentation today, you're going to love the Fusion Week. We have two really great speakers. We have Jorgen Randrup, and we have Ramona Vogt from Livermore, and then we also have Nathan Giha, great student here. So you're going to hear a lot of great stuff. Okay, so I'll just mute myself, wait a few minutes, and then I'll come back to see if there are any things in the chat, any questions in the chat. And I can stay here for another 10 minutes, so don't be afraid to ask any questions. Bye. I see your question there. I'll get back to that in a second. But yeah, that's a good question. The Fermi Gas Model of the nucleus. Let me just finish checking. I'll just check one thing. Goodbye. All right, sorry, I was just checking my calendar to make sure that I could stay a few more minutes, but I can. My next thing is going to be in a while. So let's see, Fermi Gas Model of the nucleus. Okay, so let's see, Fermi gas. That's something that we usually use in solid state. That's really originates from when you try to describe electron clouds in in a solid. And so basically, the Fermi gas model would describe. Well, I don't know if you're familiar with like concepts like the Fermi surface and like the population of the fact that all these particles are like the Fermi there stands for the fact that they're fermions. They're all particles that have to occupy the, they have to abide by the uncertainty principle, not uncertainty principle, by the Pauli exclusion principle. And that means that as they populate levels and levels and levels, they're going to have to, oh, sorry, no, that's how I do. Okay. There is going to be some levels that they have to occupy. You know, imagine it, just like we did in the beginning with the building up the nucleus from smaller and smaller, like from one proton at a time. You can imagine that you can build up the nucleus, and every time there is some energy imparted, some energy imparted, some energy imparted. And you know, every time there is going to be only a certain amount of like there's going to be a surface, like in some kind of energy space, which dictates that all the levels below it are going to be occupied, and all the levels above it are going to be unoccupied. There are still levels up there. It's just that there is no particles occupying it. And what happens is that in the Fermi gas, it's a really nice way of understanding statistical concepts of the statistical behavior of the nucleus. So if I want to understand, for example, how much, there is actually a quantity called the temperature of the nucleus. You know, because there is a quantity called temperature and there is energy, of course, there is a quantity called the coefficient of thermal, what is it called? Thermal capacitance. And so it's like how much energy do I have to put to raise the temperature by a certain amount? Now the temperature is more related to the entropy properties of the nucleus, but the Fermi gas really does describe like how do I go from a inert state to exciting higher levels, you know, in the above the Fermi surface. So I know this is a kind of like self-referential, but it's I mean, I don't know how much we can cover in just a few minutes here, but it is extremely useful. One thing, for example, one way that is very useful is to understand that in terms of yeah, we said each of those states, unoccupied states, is going to have a different value of the angular momentum. So maybe this is going to have an angular momentum 1/2, 3/2, 1/2 again, 5/2, I don't know. And then you're like, okay, what is the total angular momentum as I add energy to the system? So as I remove particles from below and I put them above, what is the angular momentum that I populate? And that's how you describe it that you can describe it with this Fermi gas model, where like you extract from below and populate above and above and above. The other thing that it could be done, for example, you put two nucleus in touch. There was a very nice question, maybe by you, but maybe somebody else, about these collisions. You know, if you have two nuclei touching each other, how much energy are they going to share? Well, you know, are they going to be in thermal equilibrium, or are they going to be in energy equilibrium? You know, stuff like that. So that's the kind of frame or reference that you would use when talking about problems of that kind. That's one of the things, you know, like I know one of the things, backshifted Fermi gas is something that I've heard before when I referenced to the Fermi gas model. And I'm not sure exactly how to interpret it, but it is about these surfaces and like excitation, field levels and unfilled, but very much real levels of it. It's a simple question. Every nuclei wants to get in a stable state, and iron is the most stable nuclei from that state. So is it possible that all unstable nuclei in stage will eventually become iron? Oh, okay. Is the most stable nuclei? Yes, it is the most stable nuclei. Well, here's the thing. Yeah. So the answer, as I know it, as I understand it, is no. Stable. There are such things as called stable nuclei if proper environment exists. That's part of your question there. So if you mean in vacuum or in a perfect environment or in an environment designed to make them decay, and those environments being able to be designed by human in the 21st century. Well, you can think that all unstable nuclei. Well, no, unstable nuclei. The crudest one. I don't even know. I'm thinking that probably the decay properties, even in these extreme things inside the core of the sun, It's hard. It's hard to say. I really don't have a lot of intuition for astrophysical processes, but I don't think they would all converge to iron. I would think they would converge to stable nuclei. And yeah, it is possible that some stable nuclei might be in such extreme, like you're not gonna get uranium-235, which is unstable, decaying to some path into iron. It's probably more likely that it's gonna just find a way to become a stable nuclei up there. So if it can, it's going to try to become a stable nuclei that's close to it, because as soon as you hit a stable nuclei, you're not going to decay anymore. So I think what's interesting about this, so on Earth, it's not going to be a problem. Now, what's interesting about this is like how can you make a nuclei unstable in the proper environment? I think there is some research done on that. Of course, with the right fields, you can do it. But I don't know if it's, I don't know. Like, I mean, I don't think in the middle of the sun it's possible. But that's like, some of the hardest questions that we face. So who knows? Yeah, my answer is, I don't know. Like my question to, does it possible in normal situations? No, it will decay to a stable nuclei similar to itself. But is it going to be possible to get stuff like that? Maybe humans are going to be able to do it in like 3,800 years or something. Yeah, sorry for the long question. Adil, yes, of course, I will share them. I have to ask the person who's in charge, like who really knows how these things are run, and I'll ask them exactly where to upload them. I think there's going to be a Google Drive. I'll do it definitely tonight, or even this afternoon. So yes, absolutely. Okay, so let's see, 2:37. I am gonna stop recording